So, Assalamu alaikum students, and welcome to lecture number 14 of week 7 of Advanced Nanomagnetism course. So, in this lecture, we will learn about the spin class in nanoparticles, or it can be extended to nanowires if you understand this, and also in thin films. So, in the previous lecture, we have learned about the basics of spin glass, the main ingredients of the spin glass, as we already know, is the randomness among the spins and the frustration between the spins. And there are a lot of energy barriers, a landscape of energy barrier among the spins, and we have just metastable state. And in nanoparticles, there can be of two types of spin glass behavior. One is the super spin glass, and the other one is the surface spin glass. So super spin glass occurs when the nanoparticles are diluted or present in some non-magnetic matrix, and they have interaction between them, dipole interaction between them, which is frustrated, and also the spins are randomly. So this is called super spin glass, because the interaction is between the super spins of the nanoparticles. So it is similar to the atomic spin glass. The only difference is here we have a super spins instead of the atomic spins. So in the other case, you can see the spin glass behavior or frustration disorder can be present on the surface of individual nanoparticle. Here's the example of ferromagnetic nanoparticle, in which you can see the core behaves similar to the bulk material. Alignment is very nice, but if we go to on the surface, we have a disorderness and broken bonds. Due to these broken bonds or dangling bonds, we have a frustration among the spins. So we can have a spin glass like state on the surface of the nanoparticle, and this is called surface spin glass because it occurs on the surface of the individual nanoparticle. So super spin glass, if we read about little bit about more, a super paramagnetic nanoparticle consists of hundreds of few thousands of atomic spins coupled together through exchange interactions. Each particle have a giant superspin moment, as I told you, from the core of the line normal spins. Super spin glass behavior is related to the random freezing of such giant core spins of the nanoparticles emitted in magnetic or non-magnetic material. When we cool down the sample containing such non-percolating nanoparticles in non-magnetic matrix, the nanoparticles becomes correlated through exchange interactions, so by dipole interactions, and we can have a spin glass behavior. On the other hand, the surface spin glass behavior occurs on the surface of the nanoparticles due to the disorder and frustration present on the surface of the nanoparticles. These surface spin could experience surface spin freezing, and at low temperature, the core spins of individual nanoparticles get arrested along with randomly oriented spins. At high temperature, then the random surface spins which become frozen at the low temperatures. So in bulk, you can see this four latest example. There is some unfrustrated example, and then we have a frustrated example. So in nanoparticles, we can have a spin glass behavior, or it can be a dead magnetic layer. So at the surface, you can see that there are no atoms present above the surface layer, which are available for the bonding. So the zero field cool curve is basically is used to see this any curve. You can see this is an example of nickel ferrite out of phase susceptibility curve, zero field cool curve, in which the high temperature peak corresponds to the blocking temperature and the low peak corresponds to the spin glass peak. So this is from the bulk, and the low peak comes from the spin glass. So spin glass research started in the 1970s after the discovery of Skinner and Marosh of the peak in the susceptibility of diluted iron gold alloys, as we discussed in the last lecture. So some signatures of the AC susceptibility is presented. You can do the zero field cool measurement, and you can have a peak, and sometimes this peak is overlapped with the broad peak of the blocking temperature. If they are well separated, blocking peak and spin glass peak, then you can see them very easily. AC susceptibility measurements with frequency dependence. If you have a frequency dependence, this can be understandable. The thermodynamic magnetism can be done, temperature dependent hysteresis, and all these memory experiments and all this stuff can be done by square magnetometer. In the spin glass, in the zero field cool, you can see see a low temperature peak, separate peak if the blocking peak is well separated from the spin glass peak. This is taken from different literature. You can see for the nickel ferrite we have presented, and another signature of the spin glass in AC susceptibility. You can look these peaks. You can see this TD is the blocking peak, and the other one TF is the spin glass peak. So this is the example of nickel ferrite nanoparticles embedded in silica matrix or coated with silica matrix of 8, their size is 8 nanometer. It's very clear, 2 peaks. So here's an experiment in which the effect of applied DC field on the spin glass peak. You can see the blocking peak is shifting, the broad peak is shifting towards low temperature due to the change in the two valley exchange in a stropy barrier. However, the spin glass peak, which is very metastable state, remains same at high fields of 500. So this is the example of the spin glass system in AC susceptibility in which we have applied the DC field. So there is also thermodynamic magnetization and the relaxation experiment, in which if we have a slow means slowly decaying magnetization with time represents the possibility of the spin glass behavior in these systems. So the HC, also the sharp increase in HC, can also be a signature of the spin glass behavior. The open, if we look the hysteresis loop, this is the other end of the hysteresis loop. You can see the hysteresis loop is open up to 2 Tesla. If the hysteresis loop is open up to few Tesla, which is very high field for the laboratory for these nanoparticles, then we have a signature of the spin glass. And this is a zero field cooled at 1 Tesla in the inset, which also is open. So this is due to the spin glass behavior. Memory effect is also important to study these experiments. So this can be done by taking 2 curves. One is taking just the zero field cool curve, and the other curve you have to stop your zero field cooling at some certain temperature, just like here at 20 Kelvin we wait for 3 hours during the cooling, and then went to the lowest possible temperature, and then take the zero field cool curve. So there is one reference curve without waiting, and then the other curve is with waiting. And on the right panel you can see when we take the difference of both these curves, we have a dip. So usually where we have waited for a long time, we have a increase in disorderness of the system, and we can have a different behavior as compared to the non-waiting zero field cool curve. On the left hand side you can see they they waited at 2 temperatures, at 21 and 27, and this is a difference delta M with the reference curve. You can see clearly 2 dips are present in this system. This is the signature of the spin glass behavior. So I hope students you have understand the lecture, and so we'll study more in detail. Okay.